In studying linear motion, we first developed a set of motion equations, and then we said what causes linear motion. And we said it is a force. Force is equal to mass times acceleration. We've been studying circular motion and have developed a set of circular motion equations, and so now it's appropriate to say what causes circular motion. And again, it is a force. Let's look at it. If I have an object that's going to be moving in a circle, all right, then the force that is causing the object to stay in circular motion, clearly in this case is the tension on the string, so it is a force acting from the mass that's moving around the circle back toward the center of the circle, okay? So let's look at the relationship. Here is a mass moving instantaneously here with this particular velocity, okay, and at some other instance with this velocity. The speed is the same, that is the magnitude of the velocity is the same, but the velocity is not the same because velocity is a vector quantity. It has both magnitude and direction, and the direction has changed. Okay, if you have a change in velocity, you must have had a force, and this is that force acting toward the center of the circle. We call it centripetal force. Centripetal means literally center seeking, or toward the center. So S of C, the centripetal force, is equal to mass times acceleration, but that acceleration must be centripetal acceleration, an acceleration acting toward the center of the circle. We want to derive an expression for centripetal acceleration. To do that, we're going to take the situation that we have and break it carefully into components. We have an object at a certain position on a circle moving with a certain velocity, or the speed, v. Okay? To designate that position, we have a radius from the center of the circle out to the position, and we have a reference angle theta, so that radius has components x and y. X and y are related to r by the trig relationships, sine opposite over adjacent y of r, cosine x over r. The velocity can be broken into its x and y components. We have a vector triangle, and theta is reproduced in that triangle. If you have a radius extending to the edge of a circle and meets at that point a tangent, by definition that forms a 90-degree angle. So if this is theta, this is the complement of theta, this angle is 90, theta is reproduced in our vector triangle here, and so the x component is v sine theta, it's in the negative x direction, the y component is v cosine theta. One last thing to note before we move to our derivation is that Vx is not just negative v sine theta, it is the change in the x position as a function of time. And Vy is delta y delta t. Okay? So we have velocities in the x and y direction combined. They form our velocity vector, which is Vxi plus Vyj, standard vector notation. And we've already said Vx is negative v sine theta, and Vy is v cosine theta. We can get rid of the sine and cosines and get to something that we can talk about the change as a function of time in that relates to velocity by taking sine and rewriting it from this relationship. The sine is y over r, the y component of the radius over the radius, and the cosine is x over r. Very interesting relationship. This is the x quantity, but it has the y direction in it. This is the y with the x direction. They've switched. So now, let's pull out the constants in this expression and isolate them from the variables. So here's our velocity vector. V without the arrow over it is speed, that is a constant, and the radius of the circle is a constant. Y is the position in the y direction, or the y component of position, that is changing, and x is the x component of position, and that changes as the object moves around the circle. Now we have an expression that we can talk about finding the time rate of change. That is, we want to find the centripetal acceleration, which is delta v delta t. And here is our expression, our vector expression for v, right? So, what changes as a function of time? X and y, as we just said. So what we have, taking this expression and rewriting it in terms of the change of that vector as a function of time, speed and radius are constant. Delta y delta t is the change of position in the I direction, and v and r are constant. Delta x delta t is the change in position in the j direction. All right? Delta y, delta t we've already defined is Vy. Delta x, delta t is Vx. Further, we have defined that Vy and Vx have trig relationships with the speed v. The magnitude of Vy is v cosine. The magnitude of Vx is negative v sine. We make those substitutions, and again we collect those things that do not change, the constants. V is a constant, so you've got v times v over r, or v squared over r. Cosine changes. Vy is a constant. We got, this v is also a constant, so we got v squared over r again, sine theta. And collecting then terms, this is our expression. We found it. This is the vector expression for the centripetal acceleration, v squared over r cosine theta I, v squared over r sine theta j. Just as v had x and y component, so now the acceleration has x and y components, which are in terms of the speed, a constant, and the radius, and then the changing angle as the object goes around in a circle. If we want to know the magnitude of the centripetal acceleration, that does not change. That force stays constantly the same in magnitude. And we can do that because this is a vector. Vectors have, with their x and y components, the Pythagorean relationship, so the magnitude of a vector, as we know, is the square root of the sum of the squares. We take each of these expressions and square them. Interestingly, v squared over r squared factors out, and you can bring it out from under the radical. It just becomes v squared over r. What will be left underneath is sine squared plus cosine squared, which is 1, an old trig identity. So we have it. The magnitude of the centripetal acceleration is v squared over r. The magnitude of the centripetal force is mv squared over r. One last little comment. Notice that both of these signs ended up negative for acceleration in the position that we have here. And that's right. That force is acting in the negative x direction, this way, and in the negative y direction. So our signs came out correct, and we have the magnitude of centripetal acceleration and centripetal force.